So what do we have still in the to-do list? So, I figure I've got enough. Oh, I didn't post the recorded lecture on uniform continuity. I should do that. We're going to finish up talking about uniform continuity today, and we'll probably run into the next time we need to talk about those again. On Friday is the last day to talk about I want to change this too. So I want to give a benchmark opportunity, and then somehow there's like still topics in the list of things to be covered, but I feel like we'll find out each time. So the stuff that we're not going to get to is stuff about sequences of functions and convergence of them, with the closing thing being continuity of functions defined by parallel series. So those things are in this PDF that's online. I'm happy to talk about that if you want to come by my office and talk about power series. The arguments are like exciting and interesting. So what are we going to do with what's left? So we'll talk about uniform continuity today. There'll be benchmark opportunity on Friday. On Monday, there's just like one more thing to talk about uniform continuity. So we'll do that. It'll be, I think, actually a nice wrapping up of how uniform continuity and compactness interact with each other. It'll be another example of compactness lets you take infinitely many things and get a finite list of things. On that Wednesday, I want to do like, maybe like a practice session for how do you actually compose these like analysis style proofs, with the idea being then like, wrapping up that benchmark. On that Friday, the last Friday, I think it makes sense to give like a limited list of benchmarks to be like, let's do those ones. Maybe it'll even be another like more collaborative view. Then the final exam is the Monday of finals week. That is right, right? Does that agree with other people's memory of looking up their final exam schedule? Okay. Apparently 1 p.m., but don't trust that. That'll be a time slot to just get whatever benchmarks finished up. And since that's so early in finals week, there's not time to have a meeting in advance to do anything. So there will be like one last opportunity on the Tuesday. I think that's wrong. I will pick a time on Tuesday that actually fits into the time I have available. That might be overlapping with the other final that I gave. And it'll just be another opportunity to finish up a few benchmarks. That seem like a reasonable schedule plan-wise? All right, cool. Then, let's talk about uniform continuity. And so the warm-up that I want to do is just prove a thing is uniformly continuous on a fixed domain. There's a function I'm going to try to show is uniformly continuous, f of x equals x squared on the domain 0 to 1. And I guess that's what we're going to do. We better start by reminding ourselves what uniformly continuous means. What does it mean to be uniformly continuous? Nice. Yeah, so what's the idea here? The idea of uniform continuity, what the word uniform means, is this delta you need to come up needs to be uniform across the whole domain. So in just the definition of continuity, at each different input you're allowed to use a different choice of delta. So the choice of delta is somehow not uniform across all the inputs. This delta can't depend on the input. So that's what the word uniform means in this context. It's uniform across all of the different inputs you can study. So let's try to prove this then. Let's let f of x be x squared, then f is uniformly continuous on 0, 1. So you know how the strategy is going to go. I better start by considering any epsilon bigger than 0. This is a very explicitly given function, so I bet I can find an explicit choice of delta. I then consider any x and p in the domain. I assume absolute value of x minus p is less than that delta. That I'll have to figure out what that delta is. And then I'll conclude that absolute value f of x minus f of p is less than epsilon. So I guess let's flip over the page and start in on it. So of course we have to consider any epsilon bigger than 0. But the hard part is now coming up with a choice of delta. If you know a choice of delta that already walks, then the proof will be automatic. So let's try to figure out a delta that walks by going off to the side and doing some scratch walk. So the function is the squaring function. So I need to say something about absolute value of x squared minus a squared. I guess the definition you gave me had a p instead of an a, but who cares? So what does that make you think of? Difference of squares. It is a difference of squares. So the difference of squares formula, what does that let you do to this? Yeah. Nice. And you can also break it up under the absolute values. Ooh, so let's see. Whenever you're doing any of these continuity proofs, your choice of delta lets you control the size of absolute value x minus a. So I already know that this piece is less than delta. But there's still a dependence on x and a, and I don't like that. So what's the domain that I'm studying? There's a fixed domain that I fixed at the start of this. Where am I trying to show this sucker is continuous? 0 to 1. So the x and a I want to study here. Where are they going to live? Between 0 and 1. Ooh, that's useful. So let's just try to control absolute value of x plus a using that. So what can you tell me about x plus a? What's the biggest / smallest it could be? Smallest it could be is 0. In fact, it can't even really be 0 because that's the close parentheses. Biggest it could be is 2. And it can't even quite be. So, because of that, that should be a plus a, shouldn't it? X plus a is in between 0 and 2. Ooh. So what can you tell me about this? X plus a is in between 0 and 2. So does the absolute value around x plus a actually matter? No, x and a are both positive, so the sum is positive. And it's less than 2. So what choice of delta should I make? That sounds pretty good. Nice. All right, so let's consider any epsilon bigger than 0. Let's let delta be equal to epsilon over 2. We now consider any x and a in 0, 1. We assume that absolute value x minus a is less than delta. And you know it's going to go in the next space because it's all the stuff that's written sloppily in the space to the right. So what do we use? We use the difference of squares rule. Well, I guess this is equal to x squared minus a squared. By the difference of squares rule, what is that equal to? And I'll leave the absolute value bars there because I haven't explained why that's useful. Oh, we don't actually need the triangle inequality, I don't think, for the argument we're using. That's less than. So that step is true by the difference of squares rule. Since x and a are in between 0 and 1, how can I get that to be less than? Well, if we're doing that, then it's since. Because you didn't use anything about x plus a, that x and a or you can use that. You can replace x minus a by delta. So now let's use the fact that x and a are both in between 0 and 1. The absolute value of the sum of those two numbers, where does it have to live? Yeah. Oh, cool, but now by our actual choice, that gives us 2 times epsilon over 2. Yeah, that's epsilon. Cool. That proof feel pretty okay? Yeah, so if you're doing something with uniform continuity, if there's some restriction on the domain, use that restriction on the domain. Nice. So, when you're composing an epsilon delta proof, if you're doing something with uniform continuity, remember your delta can't depend on your choice of inputs. So you better have control over all of your inputs. All right, so we've talked about what uniform continuity means. Let's talk about why it's good. Uniformly continuous functions had better be nicer than just continuous functions. And we've seen that some functions that are continuous but bad, like 1 over x, aren't uniformly continuous. So let's now try to check that this intuition is actually correct. And here's the way I'll start. Let's let U be a subset of R. Let's let F from U to R be a function. If F is uniformly continuous, then for every Cauchy sequence of elements of the domain, F of that sequence is also Cauchy. And in order to see that this really is going to need uniform continuity, let's think about this. Yeah, let's think about 1 over x. Let's picture the graph. And remember, Cauchy, a function is Cauchy if and only if it converges, right? It's like one of the big theorems we have. So by looking at this graph, can you give me a sequence of inputs so that which converge, but for which the sequence of outputs do not? Yeah, maybe it's more right. Because I want to address like this statement. So think about f of x equals 1 over x.
is there a Cauchy, aka convergent, sequence so that f of xn, so the sequence of outputs, is not convergent, aka not Cauchy? So maybe I'll give the example of what does not satisfy this. There's a lot of nots in there, right? So here's a sequence. It's getting close to that. There's something. So I guess the sequence of outputs, there's a sequence of points on the graph. Does that sequence of output seem to converge? Yeah. Okay, so that's not what I don't want. Is there a sequence of inputs that I could take so that the sequence of outputs does not converge? Yeah, how about something getting close to 0? Just visually, that seems sensible, right? So the sequence of output values looks like it's going off to infinity. Doesn't converge. So let's now just try to verify that. We got an intuition graphically. Let's verify it on paper. Give me your favorite sequence that converges to 0. Well, okay, maybe you don't have a favorite, but you should. What's a sequence that converges to 0? Just give me one. Sure, we can do that. 1 over n factorial. No. 1 over n would be easier, but 1 over n factorial, you want things to converge quickly, okay. So let's try xn equal 1 over n factorial. Then xn converges to 0. In particular, xn is Cauchy. Let's now study f of xn. So if f of x is 1 over x, then tell me about f of xn. Well, right, what is f? It's 1 over x, so f of xn is 1 over xn. For this particular choice of sequence, what is 1 over xn? N factorial? What's the limiting behavior of that? Diverges. In fact, it diverges specifically to infinity. So we can be more specific, but the diverges is the important bit. This diverges to infinity. So f of xn is not Cauchy. So this gives a sequence of inputs that is Cauchy that when you hit with a continuous function fail to remain Cauchy. So continuous functions can screw up the property of being Cauchy. Uniformly continuous functions don't. That's a nice behavior, and let's check that it actually happens. So let's let u be a subset of her, and f from u to her be a uniformly continuous function. That assumption is just for uniform continuity. We need to show that every Cauchy sequence of elements of u has f of xn also being Cauchy. That sounds like a universally quantified statement. So what should the boss line of my proof be? So we want to show for every Cauchy sequence xn of elements of u, f of xn is also Cauchy. So let's set up that assumption. I want to prove something is true for every sequence of elements of the domain. So what did I better consider any of? No, let's just let Xn be any Cauchy sequence of elements of the domain. Right, so just set up the logic for the problem. Let's let Xn be a Cauchy sequence of elements of U. We have to show that f of Xn is Cauchy. Ooh, so maybe here would be a good gesture, a good thing to remember. If we want to prove that a sucker is Cauchy, we better know what the heck that means. What does it mean to be Cauchy? So what does it mean to be Cauchy? To be Cauchy, it means that the terms of the sequence get close to each other. The big fancy theorem is if the terms of sequence all get close to each other, then they're just getting close to a single number. So Cauchy implies convergent, and conversely. So here's what I need to prove about f of Xn. So let's put aside another want to show. We want to show for every epsilon bigger than 0, there exists a big N such that for all m and n bigger than big N, absolute value f of xm minus f of xn is less than epsilon. And you know what? Let's try to sketch out some reasoning here. So f being uniformly continuous means that for every epsilon bigger than 0, there exists a delta bigger than 0, such that for all x and a in the domain, fair enough? So let's try to track what we want out of this. So our eventual goal do this in a way that's actually on paper. So what's our goal? Our goal is that's what we want to eventually get. That looks a lot like this conclusion, doesn't it? It's just x and a instead of xn and xn. Ooh, so if I knew this with xm and xn, then that would give me the goal. After some setup, you have to like state this line in the proof before you use it. So I need xn and xm to be within a delta of each other. But what do I know about xn? What's the assumption I put on xn?
It's Cauchy.
It's Cauchy. Ooh, that looks a lot like this, doesn't it? Delta's a positive number. It doesn't matter that this sucker is called epsilon. It could be called delta. Who cares? Aha. So, as long as n and m are bigger than big N, where that big N is chosen using the delta instead of the epsilon, that'll give us that. Oh, hey, but that's exactly a proof of Cauchiness. So I think I believe the claim now. Now it's just a matter of putting it into WANS. So the first thing we did is we translated from epsilon to delta using uniform continuity. So let's do that first. Consider any epsilon bigger than 0. Since f is uniformly continuous, we get a delta. For every epsilon, we picked an epsilon, there exists a delta. There exists a delta bigger than 0, such that for all, maybe I'll avoid even using letters that look like the letters that I have so far. For all, I don't know, A and B. No, yeah, A and B. Those are reasonably distinct letters. In U, if absolute value A minus B is less than delta, then absolute f of A minus f of B is less than epsilon. And notice I am numbering this equation. That line is now numbered. I'm going to fall back to it and call it 7.17. Plugging along okay so far? Nice. What did we do next? From this choice of delta, we used Cauchiness to get a choice of big N. Oh, well, we know how to do that. Since this quantity is delta, is positive, and xn is Cauchy, the definition of Cauchiness tells us that there exists a big N such that for all m and n bigger than big N, absolute value xn minus xm is less than delta. And the scratch mark is what told us that delta was the right thing to put there. We could have put any positive number we wanted. All right, so let's consider this quantity big N in the line above. Let's assume that m and n are bigger than big N. So notice that flows a lot like the proof of what a proof of Cauchiness should do. We've considered any epsilon bigger than 0. We've now conjured up a choice of big N. We now consider any m and n bigger than big N. Let's use that m and n. Since m and n are both bigger than big N, what does 7.18 let us conclude? Not that, right? Ooh, that's good. All right. We now have xm and xn elements of U. We have xm minus xn in absolute value less than delta. Ooh, that's all the setup we need to use 7.17, right? So what can we conclude because of 7.17? Oh, neato. And let's just have a good, strong conclusion sentence. We've done all of the work needed to conclude that the sucker is Cauchy, that f of xn is a Cauchy sequence. Let's just check off the boxes. Did we consider an arbitrary epsilon bigger than 0? Did we summon up a choice of big N? Yep. And it's not an explicit choice of big N, and it can't be, because we don't have any explicit confidence. We then considered an m and n bigger than big N. And did we get the inequality we need to get Cauchiness out of it? Nice. So let's just put that conclusion. Thus, for all epsilon bigger than 0, we have found a big N such that for all m and n bigger than big N, absolute value f of xm minus f of xn is less than epsilon. Thus, the sequence f of xn is Cauchy. Cool. That feel pretty good? And hopefully, like, it also felt reasonably straightforward. You have these ingredients, you're putting them together, your goal is a big N. Well, the only way to get a big N out of anything is the Cauchy assumption, but that connects with the x's instead of the f of x's. Well, to go from the f of x's to the x's, you need to use uniform continuity. And that was like the logic to follow. Groovy. Let's carry on. So there's one nice property of uniformly continuous functions. They send Cauchy sequences to Cauchy sequences. They also have tons of other nice properties. If you take a bunch of inputs that cluster together around a limit point of the domain, that limit always exists. Which, as we saw, 1 over x isn't correct anymore. The limit of 1 over x as x goes to 0 doesn't exist. Right? It's not even plus or minus infinity because it wants to be both. That doesn't happen for uniformly continuous functions. And let's try to see why. So let's let u be a subset of R. Let f from u to R be uniformly continuous. Let's let p be a limit point of u. I need to show that the limit as x approaches p of f of x exists. All right. So I think I'm going to use a bunch of sequences in this argument. And the motivation to do that is we literally just proved that uniformly continuous things are nice on sequences. So, step 1. Since p is a limit point of u, there is a sequence of elements of u such that xn approaches p. Right? That's something that holds true, right? I can take a bunch of increasingly small deltas, and each of those delta neighborhoods intersects u. That gives me a sequence. So let's try to play with this. This sequence xn converges. It converges to p, in fact. Well, since xn converges to p, xn must satisfy a condition that's the same as convergent. What is that condition? I just want to get the assumptions to use the theorem we just proved. What's the assumption that we used in the previous theorem? What did xn have to satisfy? Cauchy. Oh, is Cauchy the same as convergent? Yeah. That's the Cauchy convergence theorem. By the theorem that we just proved, what can we conclude about f of xn? It's Cauchy. Oh, so now let's go backwards. By the Cauchy convergence theorem, then what can you tell me about f of xn? It's convergent, yeah. So all I'm doing there is playing this game, translating back and forth between Cauchy and convergent. So it's let y be its limit. So here's the idea. I have this nice uniformly continuous function. There's the limit point of the domain that I'd like to evaluate at. I'm taking a sequence of inputs that get close to that. Oh, notice the sequence of outputs, if it's getting close to anything, it's got to get close to the limiting value. So if this limit exists, it only has one option. It is this number y. So, if we want to show that the limit exists, let's show that the limit is equal to y. And this is the type of game that we've played before, right? When we proved the Cauchy convergence theorem, first we did something to summon up a candidate for what the limit should be, and then we showed that limiting value was actually the limit. we're doing this, it's the same sort of game here. So, there's what I need to show. Let's take advantage of this as a moment to remember some definitions. Just a definition. What does that mean? The thing I just saw called informal. What's like the precise statement of it? What's the definition of the limit?
Well, epsilon greater than 0, there exists a delta such that x minus f of the absolute value of that, sorry, is less than
Cool. I left it blank because you left the thing out.
f of not just
Ooh, no, that should be blank. I want to show that f of x gets close to y. But I want to show f of x gets close to y when x gets close to p. So, I need to show this happens as long as absolute value of x minus p is less than delta, but I don't care what happens when x is literally equal to p. Alright, that feel okay? Groovy. So let's just try to unravel things. So I'll try to like draw a picture over here, down here, of the situation I want. What I eventually want is there's f of x, there's y. I want to get these things to be close to each other. And so to do this, I'm going to try to set up like a diagram that's going to let me do the triangle inequality. So, do I know something that gets close to y though? Right now y is defined to be the limit of f of xn. So, what's something that gets close to y? Yeah, right? So that's going to be less than epsilon as long as little n is bigger than big N. Fine. Should I also be able to arrange that f of x and f of xn are pretty close? As long as xn and x are within a delta of each other, right? Because of uniform continuity? Oh, cool. So that's like a complete path from f of x to y. So what do you think I want to divide those epsilons by? There are two legs. If I can get that to be less than 2, then that'll make me happy on this front. I guess I have to settle this bit. xn and x. Let's try to get those things to be close together. In particular, I guess I need that to be less than delta. All right. Well, let's see what we can do. Do I know something that xn's are getting close to? What are the xn's get close to? P. So I guess that's as long as little n is bigger than some other big M. All right. Is x also close to P? right, I get to assume that. I want to show as long as x is close to p, then f of x is close to y. Oh, cool. So that can be less than an arbitrarily small positive thing. Oh, cool. That's small, so this is small, so this is small. That'll complete the argument. Now let's just put all of that nonsense into lots. So let's try to do it. So let's consider any epsilon bigger than 0. Let's get this delta first. Since f is uniformly continuous, there exists some delta bigger than 0, so that for all, I don't know, I'm going to keep on using letters that aren't similar to other letters, a and b in U, if absolute value a minus b is less than delta, then and I can put any positive number I want there. By looking at the diagrams below, what do you think I want to put there? Epsilon over 2. Sounds good to me. How am I doing for time? I'm doing okay. All right. So I have this choice of delta. Now let's consider any x in U. I get to assume that 0 is less than the absolute value of x minus p is less than, I can stick any positive number I want there. Because you get to pick delta when you're proving something that's uniform, proving something converges. Anyone have an idea of what I want to put there? We can figure it out later if we need to. But how about delta? We have a delta. Let's just use it. I'm going to color code my delta, this delta, because I think that I will need to revise that choice once I know what goes there. So we need to show that absolute value of f of x minus y is less than epsilon. Right, that does agree with what you need to show, right? I need to show f of x converges to y. That's the conclusion I need to hit. All right, so let's play this game. Since xn converges to p, there's some big N, so that for a little n bigger than big N, I guess I'm calling it n1 and not big M. That's okay. For a little n bigger than big N1, absolute value xn minus p is less than, well, it has something to do with inputs, and right now delta has something to do with inputs. So let's put a delta there and see if we need to divide later on. Appealing to the triangle inequality then, the absolute value of xn minus x. At this point, have we established a single number that is simultaneously close to xn and close to x? Do I have xn minus something is less than a small number and x minus something is less than a small number for the same something? What's that something? P. Whenever you're in that situation, you should add and subtract that p, use the triangle inequality. That's the same thing as xn minus p plus p minus x is less than or equal to xn minus p plus absolute value x minus p. I swapped the order of those two, but who cares? Right, it's in an absolute value anyway. And let's see what we've got. What's the upper bound I have right now on absolute value xn minus p? Delta. What's the upper bound I have right now on x minus p? Add those together, 2 delta. So let's see, that means I have these two inputs, xn and x, which are within 2 delta of each other. If instead they were within 1 delta of each other, I could get those outputs to be within an epsilon over 2 of each other. So, what should I replace those orange deltas by if I want this to be a delta? I mean, I wound up with 2 deltas. So what do you want to replace that delta by?
Delta over 2.
Let's just divide some deltas by 2. So, doing so, nice. So what do we have now? We have that, well, as long as this little n is bigger than big N, we know absolute value of xn minus x is less than delta. So that means I know f of xn minus f of x is less than epsilon over 2. So all that setup came from studying this triangle. And this triangle was motivated to get this leg less than epsilon over 2. So far feeling okay? All right, let's keep plugging along. The remaining leg I have is I need f of xn to be close to f to y. Oh, but that's just like the definition of the limit, right? So since f of xn converges to y, there's some n2. Here I called it big N. But whatever, that's just an artifact of the fact that I typeset the notes before I write them in Parson. There's some big N2, so that for all little n bigger than big N2, absolute value of f of xn minus y is less than epsilon over 2. And I'm putting that divide by 2 because I know that I want to divide by 2 because of that picture. So let's put this all together. So let's now fix some choice of little n bigger than the max between n1 and n2. So let's see what we want to add and subtract. My eventual goal is f of x minus y is less than epsilon. Right now, do I already have a single number that is simultaneously close to f of x and close to y? It looks like that's close to y. Is that thing also close to f of x? As long as little n is bigger than big N1 and little n is bigger than big N2. So that's why there's the max. So as long as little n is bigger than big N2, then let's subtract f of xn and see what we get. F of x minus y is equal to absolute value f of x minus f of xn plus f of xn minus y is less than or equal to absolute value f of x minus f of xn plus f of xn minus y. And now let's just put together the individual ingredients there. So that's sucker, f of x minus f of xn. Flipping to the previous page if you got it. Do we know that that's less than something? Epsilon over 2. Is that because little n is bigger than big N1 or because little n is bigger than big N2? Just because I want to put it in the right spot.
Big N1.
So I guess that other piece is also less than epsilon over 2? Does that line up with what's written on the previous page? Cool. Gosh, xn minus y is less than epsilon over 2. Oh, cool. So add those together. This thing is less than just epsilon. That was a whole lot of stuff, right? So let's just go back through it with my remaining less than a minute. And let's just see if this actually proves what we needed to prove. So what was the goal? The goal was the limit as x approaches p of f of x exists. In order to do that, we were going to show that the limit is equal to y. So sometime after this point, do I consider an arbitrary epsilon bigger than 0? Yes, it's right there. Do I then come up with a choice of delta and assume that absolute value of x minus p is less than delta? Yeah, I guess it was the delta over 2, but that's okay. I have a positive number and I assume the absolute value of x minus p is less than it, and bigger than 0. But I guess the bigger than 0 didn't actually come up in the proof, did it? That's all right. Did I then conclude eventually that absolute value of f of x minus y is less than epsilon? Nice. Okay. Add some sentences putting that in. Closing with, thus, limit as x approaches p of f of x equals y, in particular, the limit of f of x as x approaches p exists. Neato. So, there's a bunch of nice properties that uniform continuity resolves that normal continuity doesn't. That's why uniform continuity is nice. The last thing that we're going to do is we're going to tie a bunch of the stuff we've done together, proving the following. Every function is uniformly continuous, as long as you only study that function on a compact set. That's what we'll do on Monday. Cool. Nice. So let's see. I've got my office hour still today, 1 o'clock. Anyone planning on dropping by today?